All righty, welcome to week 3 here of Collage for 2022. We'll be continuing to talk about coronal heating. Again, please feel free to put questions in the chat, and I'll try to repeat them verbally so we can all hear them without looking at it. Just looking at the participants coming in, and yeah, so we're going to continue. I guess we didn't get through all of the material from last week, so I'm going to sort of cover some of that. How are we doing here? Yeah, we talked about some of the physics of the sort of the energy requirements of coronal heating, how much energy is available, how much is transported up, and then we did a quick sort of lightning survey of many of the different physical processes that were proposed to solve the problem. And we'll do more of that next week and the week after when we concentrate on waves, turbulence, reconnection, some of the big problems in some of the big processes in the corona. We started to talk about how you can actually turn the crank, and if you know how much heating is going in, what does that imply for the actual appearance of the corona? What is the temperature and the density and all that? And I didn't get too far through that, so I'm going to now click the button and sort of skip to the chart where I talked about the various regimes. If everything is time steady, then determining the coronal temperature is really just a matter of how do all the different sources of heating and cooling balance each other out essentially to zero in the time steady limit. And we looked at the photosphere, and there was really only one term, Q-rad, the radiative heating and cooling, that has to sort of adjust itself to zero. I guess I even have just the one slide of that, but we're going to just talk quickly about some of the others. Yeah, we talked about the photosphere, where you can go through all this radiative transfer and figure out if there's a balance between photons being absorbed and being emitted. Then the energy, somebody needs to mute. The energy is essentially this difference of temperatures, and if you get hotter, if you increase the temperature a little bit, that actually pushes the radiative cooling into the negative regime, so it cools things back down, or it's basically this stable equilibrium. If you go up, it comes back down. If you go down, it comes back up. But essentially, this is really just appropriate for the solar photosphere. This yellow highlighted region at the bottom here, that is really just the optical surface of the sun. All the interesting stuff that we're going to be talking about in this course is happening higher up, the chromospheric temperature rise, and then the huge coronal temperature rise. The temperature is much higher than that, and other terms start to be important. And that's really where we're going. So when we start to talk about the chromosphere, the temperature starts to increase, and what we're now seeing is a balance between radiation, which wants to now cool things off because the temperature has now risen a bit above radiative equilibrium, so it wants to cool it back down, and then the heating, because the reason that the temperature goes up is because we've added this source of heat. We're dumping it into the plasma somehow. And yeah, so it's a balance between these two terms. Yeah, and of course, the reason that the radiation is such a big deal, when you look at the chromosphere, you see extra emission in the UV and in the optical. All this loss of photons is actually acting to cool the gas down. So yeah, so you can even go to a more extreme. When the temperature gets to be much bigger than that radiative equilibrium floor, then you can even rewrite the radiative heating versus cooling by basically taking out a factor of temperature to the fourth, and then this competition between the two is really no longer a competition. It's 1 minus a small number, because the temperature is now bigger, and everything that's left over is negative. And this is often written, basically this term in parentheses is just ignored, and everything else is written as an optically thin radiative loss rate that's proportional to the square of the density, which comes into play in the opacity of the various sources of the photons. And this temperature dependence gets folded into this function, this radiative loss function. I've plotted here, 6 different versions of it. they're compared against each other. There's all sorts of different assumptions about the elemental abundances and the physics that goes into this. So different people sometimes use different versions of this. I've got my own in there too from a 2007 paper. But really, if you just sort of squint your eyes, the basic physics of this function is that for the chromospheric temperatures of about 10 to the 4 to 10 to the 5 Kelvin, this is an increasing function of temperature. For the corona, it's a decreasing function of temperature. Don't worry about 10 to the 8 Kelvin because we're not going to really see that in the sun, in the solar atmosphere anyway. But yeah, so that's really what we're talking about here. So for the chromosphere, it's this increasing function. And if you want to figure out what is the temperature, if you want to solve for the temperature as a function of position, say, you have to solve this equation. Radiation is balanced by heating. The radiation loss is a negative term. The heating is a positive term. I talked about density squared times this function for the radiation. For the heating rate, I'm actually hearkening back to the expression I gave in the last lecture, where we expressed the heating rate as an efficiency times the Poynting flux, and this m exponent, we had the m and the n exponents for the efficiency. And I'm sort of taking only one of those factors that the heating rate depends on, and assuming everything else is sort of a constant. Many of those other factors really are sort of constants, right? The photospheric driving velocity, the size, the various sizes of things. The only thing that varies very, very strongly as a function of height as you go up from the photosphere into the chromosphere is the density, because the density is dropping like a stone by orders of magnitude every few hundred kilometers, because the scale height is so small compared to the solar radius. So the density dependence is important, and we can just take this equation. We'd really love to solve it for the temperature as a function of position, or the temperature as a function of density, because we know how the density is dropping. But really, all we can get is to this point. If this was an actual mathematical function, we could take the inverse function and of both sides to solve for temperature, but we can't. It's sort of just a tabulated function, but it still tells us a lot. If you take the values of m that we worked out last time, we found that the values of m between -1 and +2 are the reasonable range. And if you plug those in, this basically says that the value of the radiative cooling function is proportional to the local density to some negative power, which means as you go up in height, the density goes down, and this density to a minus power is something that's increasing as you're going up in height. And what we know for the chromosphere is that at least for the values of the temperature that we know exist in the chromosphere, this lambda of t is also an increasing function of t. So as you're stepping your way up through the chromosphere, and if you want to keep this balance happening at each point, that means that you have to increase the value of lambda. Well, if you're on this left side, that means you're also increasing the value of the temperature. So the fact that the temperature is this slowly increasing function of height is basically a reflection of the fact that this left-hand part of the cooling function is very rapidly increasing as a function of temperature, right? If you go up several scale heights and the density drops by an order of magnitude, then lambda is going to increase by an order of magnitude. But because it's so steep, the temperature just increases just a little bit. And that's why I have these yellow, orange, and red points to sort of guide the eye to see the fact that in the chromosphere, the temperature is rising very shallowly with height, even though the density is dropping by several orders of magnitude in this region. Well, you see, this can't go on forever, of course, right? If you know that the heating rate is proportional to something that's, this function of density, and as you go up, this right-hand side is increasing. That means the value of lambda that it wants to hit is going up and up and up. Eventually, there's going to be a point at which you're actually above the curve, and there's no more, you've actually run out of radiative cooling. And that is one of the reasons that we actually get a sharp transition region from the upper end of the chromosphere to the lower part of the corona. The temperature just shoots up because it runs out of cooling. Yeah, there's also this stability instability thing, right? When you're on the left-hand side and you inch your way up a little bit in temperature, that means if you just increase the temperature of a parcel just a little bit, that increases the cooling, that increases the magnitude of the cooling. So if you've changed nothing else, it would bring it back down. And if you decrease the temperature a little bit and you find a new equilibrium, that decreases the cooling and that would heat it back up. So that's sort of stable, like the photosphere is. But this other side is not, right? Once you reach this peak that's around 10 to the 5 Kelvin, there's really no more stable equilibrium, because if you're now on this side, you increase the temperature a little bit, you decrease the rate of cooling, so there's less cooling, which means the temperature will want to keep increasing. And this is just an unstable sort of runaway process where the temperature just blows up, and it blows up so fast that it's this very sharp transition region. This is one reason why the transition region is so sharp. It just runs out of the ability to cool, and even if it was, it would be an unstable process. Yeah, so really that's the end of what I'm going to say about the chromosphere for now. Once you get up to about 1 million degrees, we have to rethink the equation again, because there's a new kind of equilibrium, because it's no longer just a balance between radiation and the heating. Now we can say the coronal energy balance, because we also have a new component. There's this heat conduction, or the thermal conductivity of a hot plasma. And that turns out to be another important component of the balance between heating and cooling. So a lot of what we're going to be talking about today is this balance between these three terms. This is what Rosner, Tucker, and Vaiana worked out in 1978, and what Martens developed further in his 2010 paper. And we'll solve this as we go. But what I'd like to do just in the lecture notes is just to step through a slightly simpler version of it for now, because once you go up a little bit from the base of the corona, it turns out that the radiation is no longer that important anymore, because remember, the radiation had a rho squared times that lambda function. And as you go up, the density is dropping. And once the density drops enough, everything is so optically thin that the photons really don't make much of a difference to the total energy of the plasma anymore. So you can think of the balance up in most of the corona as a balance between heating and conduction. And it turns out that this simpler version of the equation is actually possible to solve for the temperature as a function of height along this loop. Another simplification that I'd like to impose here is to just assume that the heating rate is a constant. Again, this is not something that Martens does. Martens has these alpha and beta exponents to look at the spatial variation of the heating. But let's assume that those alphas and betas are 0. One way of sort of justifying this is that when you go up in height and the temperature gets very large, the density is still dropping, but it's not dropping as fast anymore, because the hydrostatic scale height that determines how rapidly the density drops is proportional to the temperature. So when that's large, it sort of flattens out. So, okay, even if the heating rate is still depending on density, it's not changing that rapidly as a function of position. So, all right, maybe it's constant. But if it is constant, then whoops, what we are left with is a differential equation, but it's actually not too terrible a differential equation. Yeah, it's second order, 2 derivatives, but it's equal to a constant. So really we can, if we're careful, we can just integrate this thing twice to get temperature as a function of the distance z. I'm going to follow, again, Martens, who defines these new variables. You can sort of non-dimensionalize the distance just by normalizing it by the length of the loop, or the maximum height. I guess this is the half length of the loop, the distance between the yellow and the red in this cartoon. The trickier variable is to take the temperature and take it to the 7/2 power and normalize it by the temperature at the top of the loop, which we don't know yet. That's still undetermined, but it's convenient to do it this way, because when you look at this slightly complicated second derivative in terms of this new y, it's simpler. It's really just the second derivative of y with respect to x. And all the constants get piled onto this right-hand side along with the Q heat constant, and it's just the second derivative of y as a function of x equals a negative constant. And I'll bet you can, I bet you can think about what the actual function y of x is going to look like if all we know is that the second derivative is equal to a negative constant. You could even pop into the chat what that function is going to look like, but we'll see it in a second. Yeah, we should also think about boundary conditions because this is a differential equation. But because we've defined these x's and y's in sort of an intuitive way, we can think about, we can sort of almost just read off what we know some of the boundary conditions to be. The value of the temperature at the top of the loop is equal to the value that we've said it is at the top of the loop. We'll call it T max. So we're just saying y of 1, where z is equal to L, is equal to 1. That's a valid boundary condition. Also, the derivative of y at the top of the loop, the temperature, the slope of the temperature, should be 0 because there's sort of symmetry. If this is a loop with 2 foot points and the temperature increases as you go along both foot points to the top, the temperature is not going to be sort of this cusp-shaped thing. It's going to be a nice, reasonable, smooth maximum. So the first derivative is 0 in that case. There's also this bottom condition where everything is cold, right? The temperature at the bottom is something like 10 to the 4, right, in the chromosphere, but at the top it's something like 10 to the 6. Well, if you figure out, if you plug those in and compute y, that's something like 10 to the minus 7, which is really close to 0. You can actually run through this and then, with the assumption that it's 0, and then plug in 10 to the minus 7 again, and yeah, it's not going to change that much. Martens has a whole section where he goes in and puts in this small number and sees how things change, and it really doesn't change that much. But the question to ask is, how many boundary conditions do we actually need in a problem like this? I've listed 3, but how many do you actually need? I'm going to wait for somebody to say something.
Only 2?
Yeah, somebody said 2. Yes. Second order differential equation. It should just need 2, right? But if you just integrate it, well, sure, there's a C1 and C2 unknown integration constants that you'll need to use those 2 boundary conditions for. But there's also this psi, this constant that contains something we still don't know, right? It's the maximum temperature. So guess what? We can use those 3 boundary conditions to specify these 3 constants. This is something you might never see in a math class on differential equations, because if they give you a second order differential equation, they're going to give you 2 constants, and that's all it wrote. But here we're slightly over determining the boundary conditions in order to determine an actual physically relevant value for this other constant. And that's the clever trick to this RTV, Rosner, Tucker, Vaiana solution from the 70s. So I didn't give the details, but if you go through and apply those boundary conditions, yes, you get a concave down parabola, because that's what you get from second derivative equals a negative constant. And the constants actually give you this thing where it equals 1 at 1, equals 0 at 0. And it's flat at the top, of course, with a 0 derivative. And yeah, that's the solution. I can leave it as an exercise to figure out exactly what psi has to be 2, because we're going to use that again in a second. But I can leave it as an exercise for you to figure out what C1 and C2 have to be. But yeah, if we know y of x, we can use the definitions and come back and get T of z. And if you're taking, in the definitions, you'd have to take y to the power 2/7 to get the temperature again. And 2/7 is less than 1. So you're basically taking this number between 0 and 1 to a small power. So it's sort of inching its way closer to 1. And it gets this characteristic shape of what we think of as the temperature, the rapid temperature rise at the base and the flatter temperature at the top of the coronal loop. Yeah. That's really the solution. We can think about some of the physics of what's really happening down here at the base, right? Because you can figure out the value of the first derivative, and that goes to 0 as you go to the base, or a small constant anyway. Then the heat the conduction flux has to be a constant. So as temperature gets very small, the dt dz slope has to get much steeper, which is another separate reason why this transition region has such a sharp temperature rise. It has to do with the heat conduction, right? This is a top-down reason. We also had our bottom-up reason having to do with the loss of radiative cooling equilibrium earlier on. So yeah, there's sort of two reasons why the same thing happens. Question about, is there a discontinuity or kink where the transition begins? Well, remember, when we solved for this, we assumed that that the heating was only balanced by conduction. When we solved for the chromosphere down here, we assumed that the heating was only balanced by radiation. The real solution that bridges these two gaps is something that's going to involve all three of them being important at the same place and the same time. So yeah, the self-consistent solution is a little more involved. I'll talk a little bit more about it, but yeah, it's I don't think there's too much of a discontinuity when everything is taken into account. But the last little bit of this is that when we found out that this psi constant is equal to 2, that means that we can solve for an actual value for the T max, which we just sort of threw in there as an undetermined number. But now we know it. We can solve it in terms of the heating rate, and the loop length, and the conductivity coefficient. And it's kind of neat that we can learn a little bit more about the physics from the values of these powers, right? If you double the heating rate, the temperature only increases by a factor of 2 to the 2/7, just 20% or something. So this is sort of telling us that heat conduction acts like a thermostat that takes large variations in the input heating rate and sort of smooths them out, or tamps them down, and doesn't make them as strong as the actual dependence of the heating rate. This is why also in the Martens paper we saw that it's hard to actually use the temperature as a function of z function as any kind of a discriminator between different theories, because the actual temperature has been affected by this conduction, and it gets smeared out by this sort of thermostat effect. Yeah. All right, I had some other things to say about this outermost region, where you can almost consider the coronal heating to be done, and the energy is only being conducted outwards to infinity by just heat conduction on its own. If you do that in a nice spherical symmetric geometry, you'll get Chapman's 1957 result of, I'll even just show it to you and not go through the math. You'll get that the temperature is proportional to the radial distance away from the sun to the -2/7 power. Yeah, I mean, I think this is kind of an outdated solution. There's really a lot more that we know about the radial dependence of temperature in the solar wind that involves the importance of the acceleration of the solar wind. It is not just conduction on its own. But yeah, it's an interesting historical solution, but I don't think we need to spend too much more time on it. We'll come back to the thermodynamics of the solar wind much more in a few weeks. Yeah, so this was the end of my slides from last week, and we had the paper to read, and now sort of the extra slides for this week. I just had a little bit more to say about this RTV model in the paper, and then I want to actually go through the Python notebook. Yeah, so I guess the Martens model and the RTV model is this really confronting head-on the idea that these three heating and cooling terms really all have to be there in this equation. I assigned you to read Martens and not RTV because the RTV paper, even though it was a classic, they didn't really explain what they were doing very, very clearly in the paper. Maybe Martens goes on the other extreme of explaining too much, but I still think it's better to have the explanation there rather than not having it there at all. That's, I think, even more frustrating. What I can do in these slides is just work through some of the math of this for the simplest version of the constant heating rate. The Martens equations has the variable heating rate, but I just put this here with Martens equation 1. We have the heat conduction, you have the heating, the energy input, and the radiation, and Martens assumes that in the coronal region, the decrease of lambda as a function of temperature is a power law that goes as this goes as this gamma. Gamma is 0.5, roughly. And this is now the new version of the differential equation. And if you go through the whole non-dimensional variables things, don't even worry about the definitions of them just yet. I'm trying to follow Martens. But the actual equation that you get is now a little bit more complicated, right? When we were just balancing conduction and heating, we didn't have this third term, and all we had was the second derivative equals a constant. Now we've got another nonlinear term involving the what I used to call y, Martens calls eta, to some power. So adding in the radiation that generated this term really makes it a slightly more difficult equation to solve. Yeah, and remember we had to add a third boundary condition in order to specify that constant. Right, in these units, that constant would be called xi over epsilon. Right, if we didn't have this term and solved for minus xi, you'd have to divide by epsilon. But here we really want to know the epsilon and the xi separately. We want to solve for both of them. So we need 4 boundary conditions to really over-determine this thing. 2 boundary conditions for the second order differential equation and 2 boundary conditions to specify these variables. The fourth one that comes in is now to look at the slope of the temperature-like variable at the base, which we assume is also very negligibly small, or 0, just like we assumed the value was also. And again, Martens has a few paragraphs of justification of that also. You know what? I'm going to skip over some of the math. I really want to get to the Python notebook and show you how these things really work in practice. So, you know, the goal of this second order differential equation is to integrate it twice, just like the other one was. To do that, you have to do a little mathematical trickery. Whoops, let me just go back. You have to do some substitutions. Then you integrate once, and you get this intermediate equation. Q is just a single derivative, d eta dx. You can then plug in all the boundary conditions into this intermediate solution, and it turns out that you can actually solve for a numerical value for one of our 2 undetermined constants, xi, which actually will give us one of the scaling laws once we put in all the real dimensionful quantities again. But we haven't finished integrating. We've only integrated once. You have to integrate one more time. So you have to solve for d eta dx in terms of this nasty function of eta, and then rearrange it to integrate again. But the nice thing is, if you do that and you integrate over the entire loop, it turns out many of these things are just pure numbers, right? This whole left-hand side is really just a number. This 0 to 1 of dx is just 1. And what this eventually gives you is an expression for the other constant, right? If you put in a gamma of 0.5, you can work through it all and you'll get a numerical value of this epsilon. It's you know, an irrational number, because I think this is where Martens involves the complete beta function as the analytic way of writing this, but it's really just a number, right? So it gives you a certain number. So if you have numerical values for the epsilon and the xi, that allows you to specify the 2 different RTV scaling laws. And maybe I should even go back to the definitions. I hate to skip over lots of slides rapidly, but we had our definitions of epsilon and xi down here. And if we know that epsilon is 1.1 something, and we know xi is some other number, you can solve for how these other things on the right-hand side scale with each other. And if you do that just naively by taking those, say the numerator scales as the denominator for both of those expressions, you get these. But I don't think these are the best ways of expressing these scaling laws, because out of the 4 quantities here, there's really 2 that we start off knowing, and there's 2 that we start off not knowing, right? We know the loop length and we know the heating rate, and we want to solve for the temperature and the pressure. So I like to rearrange them, right? So solve for the temperature and the pressure in terms of the heating rate and the loop length in both of these cases. And this is actually the exact same scaling relation we got before, right? We had the heating rate to the 2/7, which was this thermostat effect. The constants out front are slightly different, but it's encouraging that we get something the same. All right. I guess the only other thing, I just wanted to summarize some of what else Martens did. Right. There's the new wrinkle of the heating rate that depends on position via this indirect dependence on the temperature and pressure. That's the alpha and the beta. There's also the delta exponent that pops in later to show how you can have the magnetic field expanding as a function of height. That changes how conduction works. And what I'm about to show you in the notebook is that Martens' way of writing the heating rate as some constant H times pressure to the B times temperature to the A. You can also write it as density and temperature rather than pressure and temperature. But that can be related directly to my version of the heating rate with the Poynting flux times an efficiency and these M and N exponents. Yeah, there's so many symbols. This mu is not Martens mu. It's just the mean mass per particle, mu in astronomy. But yeah, I just wanted to point that out. But yeah, I think that now takes us. I can now switch over and show you the notebook. And what I would like you to start thinking about is to start extending what's in the notebook. And I have some suggestions inside the notebook about things you can do, but please feel free to really do whatever you like. I mean, I just want to do whatever you would prefer to do that helps you understand the physics better, right? And whatever you'd like to do, I'd like to see something in about 2 weeks, and we can discuss it in a different channel also. So let me just switch over and show you the notebook. So you can get your own copy of the notebook on the Slack channel and also on the web page. And this is now just running in Jupyter. So yeah, I just wanted to sort of step through it. I've seen some other professors do this and very deftly edit things and rerun things on the fly. I don't know if I'm brave enough to do that. I'm really only learning Python in the last few months here. So I sort of started to write this all in IDL and translated it all to Python. So forgive me if the programming isn't as elegant as it could be. Maybe that could be one of your modifications is to really improve the efficiency that way. But yeah, so one of the first things I'd like to do is to implement the Martens equations, but do it for a typical active region loop as Carl Schreiber defined in one of his papers. So basically, after we import the packages, including special functions, we need that beta function, and define some constants, which I tend to prefer CGS units. I set the desired properties of Carl Schreiber's active region loop, right? He said that, the typical active region loop that has a magnetic field strength of 100 Gauss, a length of 30 megameters, has a maximum temperature of about 3 million degrees. So that's sort of the target. So that's where those are the constraints that I'd like to put in. So rather than, even though I just showed you solving for the Tmax as a function of the heating rate and the loop length, I'm going to turn that a little bit around in this very first bit of it, because we can solve for the heating rate and then we can figure out how realistic is that heating rate. So there's some other constants, right? If I want to use my M and N notation, we'll have to look at the length scales and the characteristic velocities at the photosphere. There's constants like this kappa conductivity constant, and Martens chi naught, which is the thing that normalizes the radiative loss function. Temperature at the base is the 10 to the 4 Kelvin, sort of in the chromosphere. I tend to use Pete, P-I-E-T, as a subscript for Pete Martens's versions of these constants. Like G, Pete is going to be his gamma exponent of the slope of the radiative loss function. There's also the other gamma, the adiabatic exponent for an ideal gas that's 5/3 that I call G adiabatic. We'll use the solar surface gravity in a bit. The only other thing I said here was that we saw last time that when you're in sunspots and very strong magnetic regions, that can suppress the convection. So the actual characteristic velocity can be reduced when the magnetic field is strong enough, and Schreiber gives this exponential formula to take that into account. So the first thing that is done in the notebook is to just take an initial guess for these exponents. Let's assume the m and the n and the delta are all 0. And then I've got this block of, this is basically the scaling relation block where the m and the n turn into alpha and beta. And then there's all these intermediate things, the nu and the mu, the lambda, the b sub lambda, which is the complete beta function. I tried to put in equation numbers from Martin's paper when possible. And then there's these constants, and I plopped in a bit of LaTeX here just to show you how the constants are defined and which of Martin's equations they correspond to. But eventually it comes down to the solving for the maximum temperature and the pressure in terms of the loop length and the heating rate. Martens is normalization for the heating rate. And yeah, you can verify that these things all work out. And so but now the first thing that I did was turn this on its head. So if we know Tmax, we can solve for the heating rate constant. And one of the things that I've got 8 different suggestions throughout the notebook of things for you to try. One of the things you can do is then take this and put it back into this original formula and make sure we get back that 3 million degrees that we put in, just to make sure everything has been done consistently. And we can also, by the way, we can take this and compare it with that simpler version that we looked at, about a half an hour ago without the QRAD term, and see how the scaling, how the constants compare to one another. But what we really want to do is now examine this heating rate that we've defined. So we can figure out the base pressure, convert that into a density and a mass density, just assuming pure hydrogen ionized gas. And then we can use those to go back into these basic equations for the heating rate, the Martens version of it. We can compute the Alfvén speed, the Poynting flux, now that we know all these things at the base of the corona. And we can compute the heat, the actual energy flux that goes into the coronal heating by taking the heating rate and multiplying it by the loop length. And we can compare that with the Poynting flux, right? This efficiency we talked about last time is just that heating rate flux divided by the Poynting flux. And we can see if the answers make sense. And again, I'm not going to rerun it, but I think it would work if I did. The flux is something like 15 kilowatts per meter squared. Remember, last time we found that the available energy was like between 5 and 50 in those units, and then the actual fluxes used by the corona was something like between 0.3 and 10 or 20. And yeah, that's in the right ballpark. And very nicely, the efficiency is less than 1, right? The fact we're not extracting more from the Poynting flux than it's actually giving us. And then there's other things you can do. You can compute the time scales to figure out if this is an AC or a DC regime. You can compute the efficiency normalization that goes out in front of that, which is what you would use if you wanted to try to apply this particular model to other loops of other lengths or other magnetic field strengths. But yeah, that's another open-ended bit there. The second thing is to actually solve for the spatial dependence. I don't know if I need to go through it all verbally. It's basically implementing Martin's equation with this incomplete regularized beta function, which has a nice special function evaluation in SciPy. Yeah, you can't solve for temperature as a function of height. You have to solve for height as a function of temperature, and then just plot them in the right way just to see what they look like. And we can do that. And when you plot it, it's very interesting that that when you compare it against the simple analytic model, that thing that started off as an inverted parabola, and then you take it to the 2/7 power, they look very close. So I was kind of surprised how well that inverted parabola thing actually does compared to the regularized beta function solution. So that's kind of nice. But what I'd like to also do here is to check the assumption of a constant pressure. I think that was brought up in the Slack discussion too. How can you assume that the pressure remains constant as a function of height? Well, we can examine it, right? We've figured out what the density would have to do if the pressure was constant and the temperature was what it is. Well, we can recompute the pressure. We can use the temperature, say at the top of the loop, to compute a sound speed. We can use the sound speed to compute a scale height. If anybody wants references to some of the hydrostatic equilibrium expressions that give you this, I can point you to them. And we can assume, we can estimate a better version of the pressure as that base pressure times this exponential damping as a function of height divided by the scale height. And we compute the density also and compare them. It looks like when we look at the pressure as a function of height, that the constant pressure is up here and the more realistic one diverges from it, but the numbers are really not that different. 2.96 versus 2.75, it's not dropping by that much. And of course, when you look at the number density as a function of height, the actual density is dropping by a lot more than the difference between those two curves. And that difference is really just way down there as a small little thing. Now, I was kind of cheating by estimating the hydrostatic equilibrium with a very simple formula. If you really wanted to do better, you would have to integrate the equation of hydrostatic equilibrium numerically. But if that's something that you might want to do, that's another thing you could do to see how much of a change that makes. The final thing that I implemented in the notebook was to explore different values of these m and n exponents to figure out, well, maybe there are some values that give you a bad result for this efficiency. Maybe that gives you an efficiency greater than 1, which doesn't make sense. It turns out you don't even need to use n, even though I specified n equals 0 above. It was never actually used at all. It would only be used if you wanted to compute the epsilon naught. So really, I'm just varying m. So really, I'm just repeating the same blocks of code here, but now treating m as an array. So basically, everything else here is an array. And I'm plotting, I figure the efficiency in the same way. And now the efficiency is the blue curve versus m, and we compare it with 1. And it turns out when we assumed m was 0, we were down here at about 0.2. And it turns out that n value is less than about 0.5. And if you use interpolation to figure out exactly where that is, it's 0.557 something. Yeah, this gives you a new range of realistic values of m. Right before, if you remember, we went from -1 to +2, but now it turns out that everything between about 0.5 and +2 doesn't seem to work with this particular requirement of reproducing Carl Schreiber's typical active region loop. I don't know. I don't know how realistic that is, but it's an interesting result. Yeah, so I guess the only other part at the end here is some more open-ended stuff for you to try. Right? Everything above was about this one typical active region loop. But what if you try to use the same model to explain both that typical active region loop and another typical, say, a quiet sun large loop that has a very weak magnetic field and is a much longer thing? Maybe it's one of these trans-equatorial loops that goes from the northern hemisphere to the southern hemisphere. Yeah, so and what I mean by consistent is that if you've chosen a value of m and n, then that means you have to use the same value of that normalization constant in the efficiency for both models. So yeah, I give a little outline of what I think the procedure probably ought to be. And I went through it in my IDL code, and it turns, so basically you want to find the regions of m and n where the efficiency for both loops is less than 1, and the temperature for the quiet sun loop is a little bit cooler than the active region loop. Not too much cooler, say between about 1 and 2.5 million degrees, just as a ballpark. And I'm giving you the answer. I'm going to show you here. I wish I could zoom a little better. Maybe I can. Yeah, so this green region is the region of m and n space where I found that all three of those above conditions actually hold. And yeah, 0, 0 is just a little bit out of it, right? But these other values are. That's another suggested thing. I've got some other things for you to explore. Maybe this delta exponent is an interesting thing because the loops don't all have constant magnetic fields. If you've been reading other papers about coronal heating, please feel free to see if they can be, if those coronal heating proposals can be implemented in the M and the N notation, and see how much they work when you turn the crank with all this stuff. There's also the base pressure, and we have observational constraints of what the base pressure does as a function of the magnetic activity of various types of solar structures. The very weakest magnetic fields, the very strongest magnetic fields, the base pressure increases by maybe three orders of magnitude or so. And I'm just wondering, what would it take to actually reproduce this plot by varying say the magnetic field of the loops? I guess that was about all I had on this. Please feel free to play around with this and see what you can do. I don't know how much else I have to say. Tom is saying about what happens when the trapped coronal plasma radiatively cools, goes the other way on the lambda curve. Does the density, what happens to the density? Yeah, there's sometimes catastrophic coronal cooling. Martens talks a little bit about the situation of a coronal heating function that is very strong at the base, but it then drops off very, very rapidly as you go from the base to the top of the loop. And that can be unstable. I think that's an alpha less than minus 2.5 or something. But essentially, that can cause, if there's not enough heating at the apex of the loop, then the plasma at the top can unstably condense and cool back down to chromospheric temperatures and become sort of a prominence up there, and it gets denser and it's heavy. It drops down, and basically this thing that used to be one loop sort of collapses down into two loops. And I think that's.
Can I show a movie of that, Steve?
Sure.
Let me share my screen. This is what Steve's talking about is sometimes goes under the moniker of coronal rain, because as you'll see, and I don't know if the audio will come. This actually has audio because it's from the NASA Scientific Visualization Studios, but I don't know if that'll come through, but the video will.
There's their standard intro.
Are you hearing the audio?
I'm not, no.
Okay, it's just sound effects in the background. But this is helium-2 and you can see on the right there was a flare followed by post-flare loop cooling.
Yeah, of course, everything I've been talking about is all this steady state assumption, but when things can change in time, there's a lot of other things that can happen.
Yeah, so there's the flare, obviously heating quite a bit. And this is helium-2 from the SDO AIA instrument.
You can start to see stuff falling down.
Yep. And it sort of appears in the middle of nowhere out there. And what's happening is there are hot loops out. So if you were to look at a hotter channel of AIA, you'd see loops there, but they're radiating in a hotter channel until they cool into this channel. And now you see what's called coronal rain.
Yeah, that's right, because the peak temperature of the EUV filter that you're looking at here is only somewhere, maybe 50,000 to 100,000 Kelvin. It's definitely below the coronal contribution.
So it's right around the knee of that curve. And if we had an even cooler channel to look at, like H alpha, we'd see the same thing in H alpha. After the 304 stuff cools, it cools into the H alpha channel and gets down to 10,000 degrees Kelvin. And you see the coronal rain in H alpha too. So this is coronal heating in reverse.
Yeah, it's got me wondering what's causing the actual spatial structure for those narrow strands.
Well, it's got to be the magnetic field, right?
Yeah. But is the field different on one strand compared to the dark stuff in between, or is it just different amounts of gas that's being input at the top and falling down in different places?
I think that's the interpretation of coronal rain, that there's an input channel at the top that's kind of dumping hot plasma at the top, which then radiatively cools like crazy because it's kind of trapped on the top of the loop. And then that cooling plasma rains down along the loops because it's still highly ionized. So it has to follow the magnetic field lines. And you get this very structured dynamic. So this is a particularly good example. And then you can see over on the right there, there's some coronal plasma condensing into what we call a prominence, kind of floating in the middle of nothing. But then that also eventually connects to a magnetic field line and rains down as coronal rain on some loops outside the active region.
Yeah, and I guess the total length of that larger loop is so big that the other end of the loop is really just not even causally connected at all to what's happening on that near side.
Yeah.
Again, that's the time scale of, how long does it take for information to propagate along these loops. Yeah, you can start to see them coming down on the right a little bit.
Yeah, I wish they put a clock on this. I think it's what we've just watched is on the order of hours. Like I would guess 6 hours, but it's not, I'm not sure of that because they didn't include a clock on the movie, which should always be on a movie of the sun, in my opinion.
Yeah.
But
Oh,
yeah,
that's nifty.
so
there
you go. That's one of my favorite things to study is coronal rain and prominences, because it is that catastrophic cooling regime that all of a sudden stuff just appears in the middle of nowhere out in the atmosphere.
Yeah. All right, great. Some other questions in the chat. Yeah, are these individual pieces the strands that Martens defines as strands or as individual loops? Yeah, I don't know. There's a continuing debate about have we actually resolved the true strands, the true smallest structures along the magnetic field, or is everything we're seeing still, even the narrowest things that we're seeing, are they still blurry collections of multiple strands? The high C rocket EUV imager has gotten much better spatial resolution in some of these things, and they think that they've now sort of gotten down to the most fundamental strands. But this was AIA, and I don't quite know if that's there yet.
Yeah. Open question.
Yeah, a lot of open questions here. Alrighty, well, yeah, great.
Looks like Marcel has a question too on, is coronal rain always associated with chromosphere condensation? And I guess the answer is yeah, that is what you're seeing is chromospheric condensation occurring starting from very hot coronal plasma and then following the magnetic field lines down into the chromosphere and ultimately probably returning plasma to the photosphere. So it is a mass return system that is important if you talk about the mass cycle of the entire atmosphere. There's stuff getting thrown up by spicules, there's stuff getting ejected by coronal mass ejections, and a lot of that comes back. In fact, that's another fascinating, if I can very quickly find the famous Vomit CME movie. That's another amazing thing to look at, because cooled plasma, when the density also increases like that, gets heavy. And you can really see some amazing dynamics with returning plasma after flares. Let's see.
So is the reason why the cooling material gets denser, is it really just sort of pressure equilibrium, right? If the pressure is constant, then as the temperature goes down, the density has to go up?
Yeah, I believe so.
That's the same. That's the same explanation for the convective blobs in the solar interior, why they rise and fall when they get hot and cool.
Yeah. There's a whole series of papers by B.C. Low, L-O-W, on this catastrophic cooling physics. And it's very interesting because you do get these very dynamic, heavy plasma results. It was 2011, right? I know I have the movie somewhere. Maybe it's up under CMEs here.
Well, maybe what I should do right now is end the recording if I can find the right button. All right, and then we will see you next week. But feel free to hang around, and we can look at the movie if we find it too.
Yeah, I'll try to find that movie. It's a really fun one to watch.
And I'll try to put the links to them in the bottom of the YouTube channel too.